All right. Let me find my place. Today we're going to talk about special collisions. So in momentum and conservation momentum, we've been talking about different collisions, and that's kind of where conservation momentum happens when two things collide and they either bounce off each other or maybe they stick together or whatever happens. We call them collisions, and then we can use conservation momentum on them. We have two special cases that we want to talk about. Elastic collision is the first kind of collision we can have. Elastic collision is a special case where the kinetic energy of the system is conserved. So in many collisions and most collisions in life, kinetic energy is not conserved. Oftentimes the kinetic energy is going to be converted into heat, in which case some of the energy dies off, but momentum will still be conserved. Even though kinetic energy decreases, momentum will still be conserved, and so we don't have to worry about it. But in the elastic collision case, we're going to assume that kinetic energy is conserved. And so what this allows us to do is it gives us a second equation to work with, and so we can actually solve some momentum problems with less information, assuming that we know that the collision is elastic. So here's an example. Two masses are moving towards each other. Mass 1 has mass 3, and the other has 8. And it's traveling at 8, and mass 2 has 6, and it's traveling at 4. And there should be a negative sign here. We're just saying it's the opposite side way. It's just kind of copied weirdly, so it's a -4. The masses then make an elastic collision. Okay, so we have this extra piece of information knowing that the kinetic energy is conserved. And the goal is to find both of the final velocities. And so beforehand, if we just had momentum, we would know that the m1 v1 naught plus m2 v2 naught is equal to m1 v1 final plus m2 v2 final. And this is still true, so let's go ahead and solve this equation by plugging this in. Our two masses are mass 3 and mass 6. So we have 3, and 3 is traveling at 8. So 3 times 8 plus mass 2 has mass 6, and it's traveling at -4, we said. It's a -4 there because we're carrying it from over here. So -4. And then we have mass 1, and we don't know its final velocity, and we have mass 6, and we don't know its final velocity. And so if we look at this equation, we can simplify. We get 24 minus 24 equals 3v1f plus 6v2f. And so we get 0 equals 3v1f plus 6v2f. But if you remember from algebra, if we have an equation with two unknowns, it can't be solved. Okay, we need another equation, and this is where the idea of elastic collision comes into play. An elastic collision means that kinetic energy is conserved. And so we have to go back a unit and remember that kinetic energy is conserved. I'll go ahead and set you up the equations you're going to be using them. You want that the kinetic energy of item 1 initial plus the kinetic energy of item 2 initial is going to be equal to kinetic energy of 1 final plus kinetic energy of 2 final. So what is nice is we're only concerned about kinetic energy. We don't care about all the potential and all that stuff. It's all kinetic here. And so the kinetic energy of both the objects beforehand added together is going to be equal to the total kinetic energy of the two masses afterwards. And so the equations look like this. It's 1/2 m2 v2 naught squared equals 1/2 m1 v1 naught v1 final squared plus 1/2 m2 v2 final squared. So again, I don't think momentum is necessarily the hardest unit mathematically, but yeah, it's a lot of writing. I get it. That's the way it is. That's why it's going to be a shorter unit, because I want to get over all this extra writing, okay? So that's the way it is for this unit. We're almost done. This is the last day of notes. So let's plug in our numbers. We know it's 1/2 of our mass of 3, and its velocity is 8 squared. Mass 2 is 6, and its initial velocity is -4 squared. Mass 2 is 3, and we're looking for its final velocity. And mass 2 is 6, and we're looking for its final velocity as well. We can simplify these terms. If we put into the calculator, let me open up my calculator. 8 squared times 3 divided by 2 That's 96 right there. For negative 4 squared, remember that the negative is inside the square, so it's going to get canceled out. So we just get 16 times 6 divided by 2. We should get 48 there. And we get 1/2. So we're left with 1.5 V1F here. So if you multiply 3 times 1/2, you get 1.5. And we're left with 3 V2F squared here. And so 96 plus 48, we get 144 equals 1.5 V1F squared plus 3 V2F squared. So now we have two equations with two unknowns. So how do we solve this? We're going to do the substitution method. We're going to use this equation over here, all known as 1, and we're going to solve for one of the numbers and then plug it into the other equation. So let's solve for V1F. We want to get V1F by itself. We're going to subtract 6 V2F from both sides and get this. And then we get divided by the coefficient, which is 3. And so we get negative 2 V2F is equal to V1F. And so what we're going to do is we're going to plug in this everywhere we see a V1F on the other equation. Okay? So we get 144 is equal to 1.5. There's the V1F, so I'm going to plug in negative 2 V2F squared plus 3 V2F squared. And I need more room, so I'm going to simplify this over here as best as possible. We get 144 negative 2 V2F squared. So if you remember, if I have some number a, b squared, right? It's the same thing as a squared plus or times b squared. We can distribute the squared to both the terms. And so let's do negative 2 squared. Negative 2 squared, 1.5, is just 4. And then V2 squared is just this. So that's what that looks like. We get a V2F squared there. 4 V2F squared. And then we need to add, I actually need more room. I'm going to erase some of the old work so that I have more room here. Plus 3 V2F squared. Let's go ahead and distribute that 1.5. We get 6 V2F squared plus 3 V2F squared. Let's combine like terms, so we get 9 V2F squared. Let's divide by 9 on both sides. We get 16 equals V2F squared. And so that means that V2F squared, or V2F, is just 4. And let's think about it. It's actually plus or minus 4, but let's think real quick. Which direction is my second mass going to bounce off at? Second mass is traveling negatively to begin with, right? And so when it bounces, if we have mass 1 here, mass 2, when they bounce, it's going to go back positive. And so it is a positive 4 here. And so we are good with the positive 4. Okay. And so we can plug that now into this equation. Negative 2 V2F is equal to V1F. So if I want to find V1F, I just plug it in. Negative 2 times 4 is equal to V1F. So negative 8 is equal to V1F. And it's my second answer. So it was a lot of work. Yes, this will be the hardest question on the test. I'll go ahead and say I'm only going to put 1 on the test. There's only going to be one question like this, where we have an elastic collision, because it is so much work, takes so long, and it is a little bit more difficult than some of the other problems. But it's important to know, it's important to see this, especially for those who do want to do something with physics in the future. This is very important to know and understand. We also have perfectly inelastic collisions. Don't worry, not only are they not as hard, but you've actually probably already done them. I kind of threw them in the last homework. They use the same equation, however, it has a more useful version of the equation for it. And so, perfectly inelastic, this slide is more important for just knowing the term now. Perfectly inelastic just means that the masses stick together after collision. It's a really weird term. I don't know why it's called that. But it just means that the masses stick together after the collision. Okay? And so if we have two masses beforehand, this is the way we would do conservation momentum. But if the masses are the same, we would normally write this, right? We would normally write V1 final plus M2 V2 final. But if the masses are the velocities are the same afterwards, that means v1f is equal to v2f. And so just like when we did some of the mass stuff before with like gravity, and we knew the masses were the same, so we just called them the same thing, we're gonna do the same thing here. Instead of calling them two different things, just call them vf, because they're the same velocity. And so if we do that, then we can see clearly, if we just call them the same thing, that we can combine like terms. We can add the coefficients. It's the same thing as if we had 2vf plus 6vf. We just add the coefficients. So that's what we're doing here. We're adding the coefficients. And so that's where this comes from. It's not necessarily important to know exactly where it comes from, but you should be able to use this equation to solve for your problems. So let's try one. A 0.15 kilogram baseball is thrown forward at 22 meters per second. A gun then fires a 0.05 kilogram bullet in the same direction of the ball's motion at 300 meters per second. The bullet embeds itself into the ball and the two travel together afterwards. There's a typo there. What is the final velocity of the two masses? And so because after the collision, they are moving together because the bullet is embedded into the ball, it's a perfectly inelastic equation or collision. And so we can go ahead and just use this equation. So the two momentums beforehand, and then the single momentum afterwards, right? There's only one object afterwards, and so we combine their masses and its velocity, and that's the momentum of the one object. They're moving together as if they were one object. We can plug in the numbers. We know the baseball was traveling at 22 meters per second beforehand, and the bullet was traveling at 300 meters per second beforehand. We combine their masses. If we add those together, we get 0.015 plus 0.05, which is 0.2. And we can look for the final velocity. And so let's throw this into a calculator. 0.15 times 22 is 3.3. Or 33. No, it's 3.3, my bad. Okay. And 0.05 times 300 is 15. And that's equal to 0.2 VF. So plus 3.3, we get 18.3 equals 0.2 VF, and then divide by 0.2, we get VF is equal to 91.5 meters per second. And so, which should make sense. The bullet is obviously going to slow down a lot. It embeds itself into this lower ball. It's going to slow down. It goes from 300 to 91.5. But because of that extra speed from the bullet, the baseball does speed up. And it speeds up to about it speeds up from 22 meters per second to 91. And so they meet somewhere in the middle depending on their masses. Obviously, the bullet weighs a lot more, and so we're going to be closer to the baseball's velocity than the bullet's velocity. And so that seems like a good number for us. That's really it. Momentum is not, we could go deeper into momentum if we had more time, if I thought it was more interesting for this course, but I think it's better to stop here. This is the last day of notes. We'll do a review next class, and then we'll have a test. And so this test is coming up a little faster. Just because momentum, there's really not a lot to it. You know, you saw that we really learned all the equations the first day. The main equations are P equals mv and delta P equals F times T. All the other equations come from the fact that of conservation momentum. Momentum before is equal to the momentum afterwards. Okay? They're not really equations in themselves. They're just laws that we put into equation form. And so there's really not much more to talk about with momentum unless we can use calculus or whatever, but we're not going to do that in here. So we're going to keep it simple. And so you have an assignment to do today. You can expect a review next class, and you can expect the test sometime Wednesday or Thursday next week. And then we'll dive into the next unit. It'll either be waves or electricity. I'm still deciding exactly which one I want to start with next. And so it'll be one of the two. With that, I'm done.